Hello, this is Babak Parkideh from the University of North Carolina at Charlotte. I'm happy to present on behalf of my team the project that's funded by Power America. So the title of the project is Extending the Power Electronics Teaching Lab, Incorporating Wide-Bandgap Semiconductor Switches and Circuits. And in this presentation, I'll go over the objectives, backgrounds, accomplishments, and outcomes and deliverables that we had for this project. So first, the objective of our project was basically we wanted to transform the traditional hands-on educations of power electronics. So our approach was looking into how a traditional power electronics lab operates and see how we can improve the learning outcomes. So one of the features that we have done for this particular project, obviously, to incorporate wide bandgap, so newer technologies that we need in education from existing silicon-based technologies. Then the hardware, typically what we have is a fixed design with limited reconfigurability. So this requires like significant capital and maintenance effort to operate the lab. And then what we have done basically by modular approaches and plug and play system, we thought that this could help us to operate the lab more efficiently with the improved outcome from the student achievement point of view. The other hand, the accessibility, again, because traditional power electronics labs are with fixed setups, right, only available usually locally. So we're thinking how we can make them possible, at least, available to public or wider audience, and possibly remotely. So let's see what we're doing at UNC Charlotte. So we start the power electronics education early on, sophomore year, when the students get to design their own simple circuits using, printed circuit boards. When they come to the junior design, basically I teach them how to design a fully closed loop controlled solar PV inverters. So there are 80 students in the class, two electrical and computer engineering majors, and they team up to design the inverter from scratch. So last year, for instance, we design, built, and implement 20, inverters. 19 out of them work as expected. So when they come to my power electronics class now, then we can talk about semiconductor physics, more advanced technologies and circuits. So our approach for this project essentially was with the goal of doing it yourself, and it was divided in two sections, hardware and lab access or control part of it. So on the hardware side, as I said, we're thinking if we can have some modular and plug and play systems, we can basically generate multiple topologies, right? And we can create a number of experiments. At the same time, the hardware needed to be rugged, compact, handy, with all the protective measures. So then we needed to create content, right? So if someone wants to develop its own modules, they can. So in the lab and access, we basically create a number of videos, manuals, right? So that the students can learn, and also possible for them to do some of those at home. We also try to reduce the gap for coding efforts that students usually struggle. And again, all of this happens because of our do-it-yourself philosophy. So this is the first generation of our system. So it consists of a motherboard, and a motherboard takes in different daughter boards. And these daughter boards are used for different circuit implementations or device characterization. So the motherboard has the section for microcontroller, and the microcontroller is connected to different sensing and conditioning circuits that basically process those signals and generates the PWM signals to control the daughter boards. So we figured that if we create two sets of daughter boards, it's sufficient to create a number of experiments. So one of the daughter board types is double pulse tester. With this module, essentially what we do, we teach the difference between the devices. So we can characterize different silicon, silicon carbide, and gallium nitride devices. The other types of daughter boards are half bridges. With one, we can build basic DC to DC converters. With two, we can make DC to AC inverters. And with three, we can make three-phase converters. And with four, we can connect more DC sources while connected to the AC side. At the same time, we can make more sophisticated DC to DC isolated converters, such as dual active bridge. So while we are doing this, basically we conducted a number of surveys so that it can help us to improve the content and the hardware setup as well. So out of this surveys and what we have seen and observed in the experimentation, we had more than 150 students in the past year to test these. Basically, we came up with the second module, so we made it like a education console. So it's like a console that takes in several daughter boards that process the power, and then the students can access or probe it externally. At the same time, we can connect some processing units, again like a module, so the students has the opportunity to test and change many of them. We think that this console is basically sturdy enough, and all the protection measures have been considered. So it has more applications and more suited for what we are looking for. So the do-it-yourself, as I said, basically has different sections. So hardware design, so we have created a depository where we have the schematics, layout, and also the user guides, how one can actually implement one of those daughter boards if he wants to. At the same time, we have lab manuals. So basically we can have our consoles ready with all the labs manuals that one can test or conduct experiments, such as device characterizations, DC to DC back converters, all the way to closed loop controls. On the controller side, we also create another one so the students can actually build and do some of these works at home, do the processor in the loop with their hardware, and either send it back to our lab or just connect it remotely and conduct some of the experiments using our hardware setup, and it became very handy, especially during COVID-19. So what we are offering at the moment, basically a complete package, including a schematic, layout, manuals, and the several videos that have created that help the students to conduct the test, including pre and post labs. So this will be offered through Power America very soon. So we hope that we make it open source to public very soon. So in conclusion, we have made a power electronics education platform or a console that allows us to teach from device to circuit levels very effectively and cover the most important part of power electronics all the way to the control part. The benefits are for students so that they can engage more, they can design their own systems, they can decide where they want to actually learn more. And from the system operator or lab manager, I think it's a very low maintenance system. So maybe one daughter board's not working, so it doesn't have to basically purchase or acquire the whole system. At the same time, the design packets and lab manuals are prepared in a way that can be complete, comprehensive, and hopefully remotely accessible. So in conclusion, I think we We need your feedback and support. We would like to evaluate that at your center. More modules are obviously possible. I think we can upgrade it with your technology soon. Thank you.